Hello, and welcome back to Old School Coding, where we're using the tools of the 1990s and the coding styles of the 1990s and the languages of the 1990s to build a signal-based simulator for a microcomputer system of the 1990s. So old school, trying to avoid using stuff that is too modern, which means that this next bit, I'm not going to really be highlighting the code that went into it because for this, I had to escape from the old school paradigm. I do not have the tools available now that I had then, partly because I am not a major corporation and cannot afford the rather expensive commercial off-the-shelf tooling that we used to display logic analyzer traces. And I went into this before, showed the display of signals. I have now updated this to include multi-bit data. Now, there are some things that we could do back then that I still can't do in this tool set. We'll get into that. So the change allows us to do things like this plot here, where I'm showing the behavior of the 8228, and I'm saying, well, I have an incoming data bus with this value here, and this says that during a fetch cycle, this is driven into the chip, so we are recognizing the status strobe says, look at the data, and A2 is the thing. And this confirms that for a sync cycle with status strobe hitting us with A2, we are confirming that when dBn goes up, we will be asserting the memr signal low. With A2, there's our data. We had the rest of this before, now we have A2. We have A2 ended by hold, and we can go down through here and we can compare all of the data signals. And I've done that offline manually, and things are correct all the way down here to status 2B is interrupt acknowledge with wait. So, yeah. All sorts of things. But the interesting thing is when we get into this part on the right, this is the trace that we've been building up for the 8080 as we cycle it through several instructions. And previously we just had a whole bunch of lines going up and down, and it wasn't really clear totally what was happening. So I have added the address bus and the data bus. I have added a trace of the program counter, which since we now have the ability to trace the content of a multi-bit signal, and the program counter is architecturally visible, that is, it appears on the pins during certain parts, but it is something that's programmatically accessible inside the 8080. So I'm modeling anything inside the 8080 that a programmer would be able to see, and that includes PC. So we can see here that we've come out of reset, PC is set to 0, and before that, I've chosen to show it as high impedance. I am not yet differentiating between the Z state, which is high impedance, and the X state, which is I don't know. And I don't know would be all sorts of hash marks. But for now, PC has a well-defined value of 0 starting at this edge. And at this edge, it transitions to 1 and so on. So here's our reset cycle. Resetting goes up, and at the appropriate time during the clock, reset goes low. And at the next appropriate time during the clock, the internal reset signal is going to go low to say, oh, we're coming out of reset. We're finally acknowledging that we're coming out of reset. And that's where we get the PC is 0 by that point. It may be set to 0 before that. And then on the rise of the next cycle, we say, oh, at the appropriate time, we are going to issue the sync pulse. Oh, also notice that the status strobe is being driven by the clock generator chip. And when we come out of reset here, when the clock generator synchronizes reset, it also releases status strobe. So we issue a sync pulse, and we've got A2 on our address bus. We are emitting the proper status. We are emitting the PC here, so the address bus here has the program counter, which will go and do its fetch. Meanwhile, behind the scenes in the T2 cycle, somewhere in the T2 cycle, probably here, we're incrementing PC. Now, this is actually internal to the PC. We've brought the address into a latch and an incrementer, and that is providing the incremented data back to the register bank, which latches it into PC. And I am not going to simulate in detail the behavior of the register select and latch logic because that is not visible anywhere. So we're just going to say that on the Phi 2 rising, we're going to do whatever it is that's going to happen, which takes the 8080 across all this time. So boom, we've incremented the address. And down here we can see, wait, got asserted here. So DBN went active and the ROM came back and said, oh no, we don't have data. So that's actually ready in, RDY in. There's a weakness in the simulation here. I cannot have multiple sources dragging ready in low because the ROM is going to set it high, and we don't deal with that. So first of all, so for this test, we're starting ready in low, and the ROM will eventually drag it high, giving us one wait state, and DBN gets stretched like this. We're going to see little teeny edges on here because the way I am implementing this to get control back to the ROM to let it say we don't need another wait, we're sending another edge. I've covered this when I talked about the ROMs. So during this second cycle, when our ready is going high, so ready goes, we send out a ready in is high, and we send out, here's the data. So our first instruction's an FB. And we have now come out of reset, and that's a mislabel. This is actually coming out and it's doing a, it's going to mess with the enable, disable instructions and a no op and so on. Let's go down to the second plot. This shows us coming out of reset. The second plot shows us executing a few instructions. So we've come out of reset and we fetch at 0. Here's the address bus, here's sync. There's the A2 saying this is an instruction fetch. Here's DBN and wait, and we get back the data from the ROM. And down here, we have also said we are going to expose the instruction register. This is not something that is program visible, but having it visible on the trace will help me debug any problems that go on. So we should see FB appearing on the data bus here, and we latch it into the IR here. And we're doing that, well, we have a choice. We can either do that on the rising edge or the falling edge. Rising edge, we might be triggering before the ROM triggers. So on the falling edge of memr, the releasing edge of memr, which is the falling edge of DBN, we're going to latch the opcode data. So we need to make sure that we latch that before the ROM sets this to high impedance. Well, I wave my hands over some things. When you set this data bus to high impedance, it will mark it as high impedance, but the value is still there. So you can still look through something high impedance to get the value that was there a moment ago. This makes it so that our simulation can continue and can run efficiently. So we have IR set to FB. This is the interrupt enable instruction. And we do indeed see here that the int E line, let me make absolutely sure I am, yes, we have audio. So the FB is enable interrupts, so this raises the int E line. Yay! So next instruction comes on, and it's at address 1. We've already incremented PC to 1, so we come into this cycle. This is an M1T1 again, and we say sync, and it's another instruction fetch. Yay, A2. And we go back out to ROM, and ROM says, oh no, where's ready in? Okay, so RDY in this top line, this is the line that the ROM pulls low to say, I'm not ready. Come back in a cycle. Then one cycle later, we inform it via this little blip on memr that it is time to look at it again. It says, oh, the address has been around for long enough, I can give you the data. So it now gives us the zeros, which is the no-op. Goes in the instruction register. It's a no-op, so we do nothing, and then we go on to the next instruction. Instruction at address 2 is F3, which is disable interrupts. Boom, F3 comes in. We disable interrupts. What do we see up here? Oh, here's our interrupt enable pin, and interrupt enable goes low. cycle through, we do another enable interrupts. Typically, you want to enable interrupts and halt, and then somebody does something. They will interrupt you, and they will send you an instruction to execute. And typically, that will be a RST instruction, which is a 1-byte instruction that will call to one of 8 addresses in low memory. Or you can actually send a call instruction in the real hardware. And I'm going to have to work out how to make that work in the software. So now let's go down. Let's take a look at the halt instruction. That was the other one that we had already done. Halt says 76, boom, we get the PC4. This is an instruction fetch. We get the data is 76. 76 is a halt. We go up here and we say, oh, what do we do for halt? Well, for halt, we have a kind of a no-op. So the M1T4 cycle is going to be basically an X. But the next T1 cycle we go into, we have a sync here, but we see that the data in that sync is 8A. And I can go over to the guy over here, and there should be an 8A. Okay, I may not have set this up properly. Oh, I actually don't have a test case that's printing a file for intact. Let me see, did I set it up and just not put it in? 8228 fetch input read into ACK. Okay, so I didn't write out a trace for halt acknowledge, but that's okay. We have it over here. Oh, right. I didn't put a trace for it because that chip literally wiggles no control signals. That's why. So we get an 8A, which is halt acknowledge, and the CPU then dives into what's called a halt machine cycle. So during T1, we assert sync. During T2, we release sync. And then we go into TW. It's actually a specially named state. Halt wait, I think HW. And we wait in HW until we either get a reset or an interrupt. So at this point, I could issue a reset to the microprocessor and see it come out of reset again, maybe give it a different set of instructions, or I could issue an interrupt, which we have not implemented yet. And we go down to the bottom, and I thought, well, let's just call up the plotting software and say, plot everything I've done. So this is our complete cycle from coming out of power on reset all the way to diving into the halt. And the scale on this is such that I have eliminated the CLK up above. It would just be minimum with the bzz all the way across the top. I have not figured out yet how to make the grid lines appear just at the beginning of phase 1. I would love to have a grid line for each one. There are tricks you can do with phase, but I believe it assumes the signal is going to be kind of a square wave within the phase. So we couldn't get the proper shape for phi 1 and phi 2, much less the proper narrow status strobe here and so on. So to get the timing right, I need to use these very small time increments. And I wish I could just say, do me a grid where it's a grid line every 9th cycle starting from the beginning of phi 1. Anyway, we can't. So this shows us executing 5 instructions out of ROM. EI, NOP, DI, EI, halt. And I am being paged by my cat. You gonna settle down? Lucy does not like to share the spotlight. So she's going to curl up, and she's going to really want both of my hands. So I'm going to see if I can get this all set up so I can continue talking. I'm hoping, yeah, that looks like the levels are still good. I've got the microphone way out in front of me. So, next steps. We don't have any I/O devices, and I really want to be able to have console input and output. I really want my paper tape reader and punch. I want a printer and all of that stuff. So I want all these I/O devices to be out there. They don't have to be exact simulations of the various chips. I was trying to find the actual UART chip that we used to use at Sun. I did serial drivers for Sun for a number of years, and I remember that the chip was easy to use. It had a nice 16-byte silo in it where you could load up the silo and data would flow out, or you get an interrupt and maybe 3 or 4 characters that come in before you service the silo. So we could handle some very high baud rates as long as we got back in time to catch it before the silo emptied or filled. And I compared this with the standard UART for the 8080. And basically, in all of my breadboarding I did at home, I just tossed that chip. I didn't use it. I had one. I tried to use it. It was awful because they tried to do too much. All I wanted was a UART that handled RS-232 serial connections, asynchronous serial. So we're sending start bits and the data and maybe a parity bit and maybe stop bits, and that's it. And I wanted to talk to a teletype at 110 baud. I wanted to talk to a modem at 300 baud, that sort of thing. And trying to get that UART chip to do it took a lot of digging to figure out how to program it to work. Whereas the chip that Sun used, and I cannot for the life of me find it. I used to just know right off the top of my head, oh yeah, the whatever. I may have a old Sun 4300 or 4600 processor board kicking around in my back room somewhere, in which case I can go look at it and see if I can find the serial chip and maybe clean off the top and read it. But that would be a pain, because now I would be emulating a piece of hardware that does things in ways that are slightly different from the way software would do them, and then I would have to join that up with software. So my plan is to grab a couple of ports, a couple I/O ports, and I will probably grab the same port numbers that are used by one of the existing systems. And instead of emulating the chip itself, I'll just say, well, when you read from this port, we're going to tell you whether there's data available and whether you can safely send data. And when you read from that port, you're going to get the next byte of available data. When you write to that port, you're going to send a byte to the thing. And behind the scenes, I will need to take those bytes and send them back and forth either to a network socket or a pipe somewhere so that I can connect up. And I am leaning towards actually having the simulator do TCP connections to a server that I'll run separately. So I will run basically a serial multiplexer externally, where when the simulation contacts that server, the server will pop up a window of some sort, and I can type into the window or have the output, or it will pop up well, depending on what we do, maybe I will have a way of connecting to it that says, oh, I'm connecting to a paper tape. So please tell me what file I want to read from to provide data, or what file I want to write the outgoing data to. That actually argues for using something like netcat, so that we can say, when you start reading from this port, I'll just run a netcat command that says send this data into the port. Alternately, perhaps that would be built in. But with the terminal stuff, with the TTY, I really need to have something somewhere that opens up a terminal port that I can type into. Now, I can use the standard in, standard out of the simulation itself, maybe, but that only works if we have a single console. And I'd really like to be able to have multiple serial ports connected to this thing. So we're going to go with the multiple serial ports connecting to something. That way I can telnet in whatever. Anyway, we'll figure it out. The alternative is to have the simulator itself set up as a TCP server, and basically it would then have to wait until I telnetted into the simulation to have a serial console. Now, maybe that would work. I want to limit the amount of network programming that I do inside this simulator, because network programming using the tools of the early 90s was very much a thing done by people who very much understood the protocols. And at the time, I could quote to you letter and verse from the IPv4 specification. And it was natural to me to understand that, oh, okay, I'm building a server, so I need to create the socket, and I need to bind to an address, and I need to listen. And when I get an incoming request, I need to accept. On the other end, we create the socket, and then we connect to the remote guy. And between all of that call, all of the underlying protocol gets knitted up. And then we do reads and writes. I'm writing 17 bytes, and on the other end, we're going to get what we get. The whole thing about datagrams versus streams, I think stream mode is better on this. We may set up a pseudo network on this that does everything in datagrams. I don't know. Anyway, so that's where we are. Now, next step here that I want to do, well, we missed a trick. Do I want to actually do a plot for the halt acknowledge to show that it's doing nothing? Yeah. I don't think so. So what can I do here? I've got a kind of a limited window. The household, we have a house guest in, so when they get back from lunch, I will be terminating the stream. But until then, let's do something fun. Something at least that might be fun. I'm going to bring up the document. Bada bing. Let's see. Okay. So there's our manual. I think that our next step is just to start implementing more instructions. And if I look at the instructions, the next one that makes sense, let's stretch this out to 2 pages here. View 2 pages. It needs to be 2 pages with cover page, so even an odd workout, right? And this is basically the big diagram of all 8080 instructions. Well, shoot, we could do in and out, but we don't have registers yet. So what can I do that is really useful? I would like to be able to write a program that basically has a loop and reads a string from memory and outputs it to a port. And we will see that on our data plot just as a stream of bytes coming out that port. And during that test, we could then render that. But that means I want a loop, I want some registers, I want to be able to read from memory, and I want to be able to output to a port. Okay. You know what I think I'm going to do? I think I'm just going to start at the top of this list and work down. We've got the few at the bottom that are our, control stuff. We start right at the top. So move R1, R2. So what we'll do here is we've got a standard T1, T2, T3. So we have a T4 cycle. And during the T4 cycle, we're going to read from the SSS register. And during T5, we're going to write to the DDD register. And that's defined by this here. The other way we could do this would be to have all of it happen in T4 and pretend. But I'm not going to do that. Let's actually model this TMP register and do it right. So we're going to go back to one page. Going to narrow this back down. And I'm going to move it off to the right on my screen and off to the right on the video. And then we're going to turn it off because all that's important is that during T4, we're going to read the source register, and on T5, we are going to write the destination register. Let's do this. So here's our 8080. First of all, before we can actually do anything with the registers, we need to have them. So data B, C, D, E, H, L. And A. Let's put A first, just for fun. A is kind of special. So there we go. Now during power on init, actually, when the 8080 comes out of reset, the contents of those registers are completely unknown. But what I'm going to do is I'm going to use data init to set them up so that they are set to the Z state. So we need to set them up here. Find the semicolon. Delete end of line. Find the space. That equals CPU arrow that. That's P data. So we've got all of those. And now we need to do a data init on each one. Just like IR. Yes, just like IR, which there it is down there. Let's separate that from PC like that. And we need to do these in the right order. There we go. So we're going to have that. Now this is data init of the register with format of %s : register name, comma, name of the CPU. So we now have our architectural registers. This is B and C, which form a register pair, D and E, which form a register pair, H and L, which form a register pair. Now, the accumulator will sometimes be worked with as part of a register pair, but it's not consistent. For instance, the 3-bit selector for A is 111, so it's register number 7. I would love to be able to just index into an array to set these things up. So what we're going to do is I'm going to say union of struct. Oh no, if I do that, we're going to have problems. Well, I hope the optimizer is really good, because the alternative is writing a bunch of functions with macros. Thinking. What I don't want to do is write 64 separate opcode decode functions to run in T4 and have those 64 each be read for the appropriate S register and then set T5 to the appropriate writer. That might be the actual highest performant way to do it. Stupid macro tricks or not stupid macro tricks. This is going to set the tone for the rest of the implementation, I can tell. Yeah, I think I'm going to use stupid macro tricks so that I can do as much work as possible at compile time and less work at runtime. So this is going to be state M1T4, and I'm going to have another one called M1T5. No. Okay. Yeah. This is going to be Painful Macro City. Welcome to 1991. So I8080 impl, we need to have a new thing which looks like fetch. No, it doesn't. It looks like nothing. Mostly it looks like this. So this is the mov instruction. And I'm going to exclude the move register to memory and move memory to register and halt. So I call this manage most mov instructions. It's tempting, instead of using macros, yeah, the way I would have done it back then would have been to use macros and have a bunch of nested macros. So I would generate all the ones that are mov from B, And then inside that macro would expand to a bunch of things that are into, yeah. Let's write up what one state looks like before we start. Law of BB T4 is going to be move the data into temp. So this is, oh, there's some funkiness I did for data. Data is now a data type, and it's got a bunch of stuff. So now we have to use data underscore 2. And we are actually not moving it directly into B. We're moving from B to temp and then from temp back to B, which means we need to have a temporary register. And that is actually a architectural register. If I can scroll back to the big diagram that we used on our thingy, on our thumbnail, you'll notice that there is W and Z temporary registers here. There's a temporary register here, and so on. So which temporary are they talking about? It's going to come from one of these registers through register select, put it on the data bus, so it really is this temp register here. So internal architectural state, we've got data IR, we've got data TMP, okay. The accumulator is A, but there's also a latch for the accumulator, which does something special, and we'll get to that when we get to that. So really what the ADDR is doing here is it's saying we're going to do a one-cycle ALU operation. So the T4, we select the register, and it goes out onto the data bus and latches into temp reg. Then the ALU has a chance to chunk on it, and the timing control is set to say, just let this value through. So the data we read is now latched here and produced, and then during T5, we are going to either latch into the accumulator or into one of these registers. So MOV T4, I'm going to call this T4B, so it's the T4 cycle for B. So data to CPU arrow temp, CPU arrow B arrow value. So we need one of those for each one. MOV T4 of reg. We're going to use token pasting to put the register in there. Actually, let's call this RRR. It's really a 3-bit value. Now, RRR actually has a number, which we'll use for the decode. And we're decoding, if we're going to do a decode, this is 6. Do not use reg M in this code. So MOV T4 of the reg does this. And we're just going to, unlike all the other coding, I am going to put these up at the top. B, C, D, E, H, L, A. So ISO-C doesn't like these semicolons, but if I don't have those semicolons, then somebody else is going to be pissed off at me. So I need something at the end here that allows a semicolon. You know what? I give up. I'm going to do this in Python. I8080mov.org. So the downside of these F strings is that all of these braces are going to be ugly. So OB CB is equal to no, let's keep the switch. No, let's just do this. So that Python code now wrote me all of these functions, which basically are going to just do that, but they also need to pass along the correct thing here. In order to keep myself from having 64 functions, I'm going to stash something in the CPU. So during this, oops. I need another thing here, which is M1T5. In some cases, opcode decode will store Okay, so we have an M1 T5. It's not going to be used in every one, but the guys that are going to use it will just fill it in and we'll use it there. So from here, now we need to say CPU arrow next state is equal to, gosh, this is going to look familiar. Where's our fetch? Like that. But now this is T5. So we only need one T4 register for every source register and one T5 register, one T5 for every destination register. It's called Gen T4. So is there something I can do to make this more compact? Well, if I make it more compact, that's pretend to get simpler than it is. So we're going to change this now to T4, it's T5. T5 is data 2. Like that. Now, RRR is SSS, source register, and destination register. So we now have all these functions which I have generated. Hopefully they're all right. We'll have to test that. Now we can actually declare these using that syntax there. So now we just need to hook up all of the T4 arrays and T5 arrays to be the right thing. And I've been doing this behind the PDF, haven't I? Okay, so in case I showed this badly, the Python code that I was developing before your eyes generated all of these functions, which I then copied into place in my code here. I then brought up the external declarations here, and now I am going to construct the opcode. But I also want to do an array up here. I need an array that I can index into to pick up the proper T4 and T5s for these guys. And I need a dummy function to go in one of them. I think I can just do 0. Let me check the definition of that thing. Okay, so these are definitions of the functions. I need to have pointers to the function in an array of 8 pointers to functions, and that will allow me to do nulls. And T5. Now, I've been shifting over to using hex because I can no longer think in octal. I am sorry. And over here, I want to make sure I don't get the source and destination flipped. So source is low, destination is high. So DDD left shifted by 3, and SSS like that. And now we can do so all of this extra work happens early on. And in fact, I can go one step further and I can use the invalid state here. Did I expose it? I did not expose it. So get the opcode right. Okay, so PF8080 state T4 is equal to that, and T5 is equal to that. So if I have entries in both of those tables, I'll write them. So compile is failing miserably because I used PF, and it's just P. So data 2 doesn't take the arrow value. Now, I am not going to be maintaining the Python code. I'm going to be maintaining the code I generated. These go away, and these go away. And there we have it. We're not executing any of them yet, but this actually hooks things up. Now, the other half down here, when we are going into T5, I goofed on my generation of the T5s because we do need to, instead of setting state next to M1 T5, which would loop forever, we need to head back and look at the ADDR halt. We need to know that in order to terminate, we need to use this edge high of red M1 int at the beginning. So I'm going to search for phi1 rise and put that line in place. And then we're going to say state next, and we're going to delete that. And I goofed because I am a Goomba. There we go. I'm trying to envision how to test this sucker. So we don't have any way of manipulating the data. All we can do is move data from register to register. Okay, so which means that in order to test this, I'm going to need to preset the registers to known values and then move them around and see if the values are what I wanted. So I was able to do that, whoops, with only this many functions. So 14 state functions and one additional bit of indirection through the CPU to get the T5, the correct T5 for the instruction. And a little bit of extra work let's get back to this. There we go. So I am going to, in here, have a void I8080 mauve, actually BIST mauve. But we need mauve init, and now we have mauve BIST. So, context of BIST is, it is going to be executed here, probably before I do the SIGs, yeah. Oh, this is really reset BIST, isn't it? Yeah, let's separate those. Do we want to have a common trace setup for all of this? No, I think we need separate trace setups for these. It'd be nice if I could just have these guys run us through our paces and handle all the tracing out here. Yeah, let's handle all the tracing out here. So this is going to be okay, so one of the things that I've done in the trace thing is that if I do a sig plot sig and the signal doesn't change at all, then it doesn't get plotted. So let's do a void I8080 plot sigs. Let's turn off that PDF. I keep working behind it. So we had this 8080 BIST, which was huge. It had the same set of plot signals over and over and over again because each plot I do doesn't require knowing which signals change. It will plot whichever signals do change. So we're just going to do an 8080 plot sigs. It's going to plot all of the signals that are important. And if one doesn't change, then it won't go in the plot. That does require in I8080 underscore impl.h that we now have extern void I8080 plot sigs. Like that. Now this guy, come in here and he says, so we're going to pass in the pointers here. So these guys can write a program and start things going, and it will start wherever, you know, at the beginning of mem. So we'll just have to arrange for that to work properly. So when I get to the point where I'm testing jumps, I'm going to have to know where my PC is. Let's just pass in CPU and ROM sub-0. What have we got so far? Reset BIST is not declared properly in the header. So ROM cells is a byte star, not a data star. The difference here is that data is something that you can trace, and byte is just storage. Okay, so don't need that or that. Working through the errors one at a time. Oh, glarp. I think I can do that. CPU doesn't have a res in. Oh, which means that I need to pass in even more stuff here. I don't know, maybe breaking these tests out into the other files is not such a great idea, since I'm not building a single structure that has all of this crap in it. I'm not building a single structure with all that crap in it. So anything that's owned by the environment, I can just put right in here. And now we're going to have a whole bunch of errors here. Okay, so we are actually a pointer to a ROM 8316, which is an array, right? Get our pointers to arrays, right? Okay, different qualifiers. Okay. So these guys now would just need a pCPU test sys. So now they have access to all of that crap. Right. This guy has its own sig plots. This guy need to pass in a sig plot SP to plot sigs. Because we need to initialize it here. So we own the sig plot here, and we set it up and fin it repeatedly, and we call back into plot sigs to get up all the traces. And that's all that knows about SP here. Good. Now SS somehow I lost my declaration of SS. So we initialize it there and trace init, where we initialize all of the traces. And we clear it in trace fini. And we've got plot sigs, which kind of comes in the middle. And we need an SS here. And I think I can actually just, I can have a separate SS, I believe. As long as I set the session to the same thing exactly. So we'll have two different session objects, but they are going to represent the same directory containing the traces. So yes, this is a linkage between these two. How can I get rid of that? I could get rid of that by putting SS inside CPU cur test sys. Wow, how about that? Even seemed to sort of kind of almost work. So now we're doing more than just these guys. I am including EI, DI, EI in the reset test. Why am I doing that? That kind of makes sense. We're going to come out of reset and we're going to do some things. We're going to dive into halt. We're done. Okay, I need to go offline and think about this more clearly because I have worked myself into a bit of a dead end here because I can't have the reset test bringing us all the way through all of these and ending up with a halt. I literally cannot do anything after the halt test unless I do another reset or I do an interrupt. And what I'd like to do is have this sequence be done by its thing and this sequence done by its thing. So I'm going to do this offline rather than being quiet a lot, and I will talk to you all on the flip side. Sorry for the somewhat short stream with a lot of dead air and a lot of non-progress. And we will see you with something more specific once I've got things worked out. Keep it small, keep it safe, and keep it fast.